takes us to do, it's long compared to the amount of time it takes us to do a T1 measurement. So we can basically do lots of T1 measurements under, roughly speaking, constant levels of radiation. But it's short compared to how long we can keep a dilution refrigerator cold, and we can run experiments for weeks and weeks. And so over time, we can see how the radiation decays. So that's where this copper-64 source was placed. It then goes in our dilution refrigerator. It's not very radioactive, but of course, to be safe, we took some safety training courses and labeled the dilution refrigerator as such. So this allowed us to basically do calibration. We measured the decay rate 1 over T1 over about 60 half-lives, just about a month of experiments. And at short times, when the radiation is strong, the copper-64 radiation dominates, and so our T1 was only 5 microseconds. But then as time goes on, you can see that that T1 is getting better and better. What's plotted here is the rate. So going down is getting better. A lower rate means a higher T1. And eventually it saturates out at about 50 microseconds. So that's great. That tells us what the rate is doing versus time. But what we need is the rate versus power. Okay, and so to get that, this is where our collaborators at PNNL were very helpful, and also Joe Formaggio's group at MIT is using this simulation kit called GENT4, developed by nuclear physics community, allowed us to simulate what we expect this copper-64 to do over time. And in fact, what we saw is that it's not just copper-64, but there are many other trace elements in this copper which also became radioactive. And rather than having just this decay with time shown in the dashed blue, the black is actually what we had and observed. Now, I should mention, we made 2 identical samples. One of them we kept outside the fridge so we could measure the radioactivity as a function of time directly with the copper-64 that we had at room temperature. And that's how we knew the radioactivity of the sample inside. And then we simulated it here. Okay, so with that, we can take our simulations and our time domain data and create basically this plot here, which is the relaxation rate as a function of power absorbed in the material. And so at high powers being absorbed, we're limited by the C64, and at low powers, after a long time, we're just back down to the background levels of T1 that we observe. And what we can do then is say, okay, at this high power limit, based on this slope, I can extract it back. And that's basically what gives me this prefactor K. And if, to give a number, it's 800 in these units shown here. Okay, so millimeters cubed per KeV seconds square root. All right. So that's the number. And then what can we do with that number? Well, we can now use it to estimate what our qubit coherence would be if it was only due to ionizing radiation. So all of that other stuff happening in parallel, just forget about that. What we can do is just say, we know K. If we knew the power in the lab, we could predict our T1. Okay, so we can do that. We can measure it. We use a sodium iodide scintillation detector, and we put it about where the qubit would be inside the refrigerator. And, we can make measurements. And the contributions there are both due to cosmic rays or muons that have scattered and come down to the sample, as well as these radionuclides that are in the wall. And so what I'm showing here are measurements that we made showing the radionuclides in our concrete walls in this energy scale. And what I don't show, but out at a higher energy scale, is where the muons kick in. Okay. So if we look at this and just say, okay, what's happening? Well, one thing that PNNL helped us with is we sent out our fridge materials to them, and they analyzed them to see if any of that radiation is coming from the refrigerator. Fortunately, it wasn't. That's really good news, that at least very small fraction of the radiation power is coming from our instrumentation, right? We don't have to buy a new dill fridge. About 60% is coming from the concrete, or external, not cosmic rays. And then about 40% is coming from the cosmic rays. Okay, that's what we were able to discern both from these measurements and from simulation again. So with this and plugging in, what we find is that the decay rate would correspond to a T1 of about 4 milliseconds. Okay, and that's interesting because that's about a factor 10 away from where we are today. So this is a problem we're going to have to deal with in the coming years. It's not limiting us today, but it's not going to be that far away. Again, you know, we've improved 5 orders of magnitude in the last 20 years. So, you know, and we're at about 200 or 300 microseconds now for our best qubits. So that's, you know, roughly a factor 10. Now, the second thing that I found very interesting is that we can then ask, what is the quasi-particle fraction that this corresponds to? And that's about at the 10 to the minus 8th level, 10 to the minus 9 to 10 to the minus 8. And that's this background level of excess quasi-particles that we as qubit, you know, engineers and physicists, as well as people who operate other devices, see in the background. And so it looks like a very large portion of this non-equilibrium excess quasi-particle fraction is due to this ionizing radiation. Okay. So takeaway message, as I've just said, the environmental radiation will limit T1 to a few milliseconds. And I want to emphasize that's if we don't do anything, right? Of course, we're going to do something to remedy this, but it's good to know what we're fighting against. And it looks like it's consistent and basically explains at least a large amount of the non-equilibrium quasi-particle levels that we're observing. Okay. So the next step was, let's see if we can shield it. Can we reduce the impact? Now, it's a small effect in today's qubits, but we should be able to see an improvement if we shield the experiment. So one option, of course, is to go deep underground where you eliminate the cosmic rays. And that wasn't really an option for us, although I want to emphasize there are groups around the world who are trying to do this. What we could do is build a lead shield. And so we bought a lift that can lift a couple tons because the lead is quite heavy. And we, meaning my graduate students and postdocs, built this lead shield that you see here, and that will shield us from the nuclear decay events in the lab. And so we could put a detector inside that shield and show that it blocks about 77% of those nuclear decays. And that's intuitive in some sense. You know, we're not blocking the top, but we're blocking the sides and the bottom, right? So we lose about a quarter. Now, it blocks none of the cosmic rays, basically, right? Those are too high energy. And so if we look at the efficiency of the shielding when it's down, it's only 2%. Okay, it's not 0 because we're blocking a little bit from the floor, but basically it's 2% effective, and it's about 50% effective when it's up. Okay, and that's due to the fact that we're not blocking any of the cosmic rays. Okay, so it's a small effect, right? So our transmons, these had a T1 of around 50, 70 microseconds. We put in a new sample, I should say, and that had 5 transmons, so we could gather more data. And these qubits had a T1 of 70 microseconds. But that's much, much less than the 4 milliseconds being caused by the radiation. So we had to come up with a way to measure a small signal on a large background. And of course, that's been known for a long time. It's called Dickey switch radiometry. And you know, this is a technique that people use in radiometry to, you know, basically eliminate background. And it's closely related to lock-in experiments if you've done those experiments before. But basically, we lift the shield up, we make a bunch of measurements, in this case about 10 minutes. We lower the shield down, we make a bunch of measurements for 10 minutes, just measuring T1 over and over again. And then we repeat that process, shield up, shield down, shield up, shield down. And what it does is it creates, if you take the difference, you can basically subtract off effectively a lot of the background, leaving the signal that's changing. That's the concept. Okay, and so that's what we did. And we can predict what we expect to see because we know the efficiency of our shielding when the shield is down versus up. And we expected to see an improvement, a change in this rate of 1/15 milliseconds. So, okay, it is what it is. And what we measured was a change of about 1/23 milliseconds. So plausibly consistent. I want to emphasize that, again, it's tough to make this measurement because the background is so large compared to the small signal we're trying to measure. This is the raw data shown here. And what we're looking for, just to give you an idea, is basically the change of orange to black, right? And so, of course, this has to be a statistical argument. But we were able to show that it is statistically significant. And so we can conclude that shielding improves the T1. Now, it's a small amount today because we're completely dominated by everything in parallel, but we will get to the point within a few years where this matters. Now, just for people who care about these things, the statistical analysis was done using the Wilcoxon signed rank test, which is a test for non-Gaussian distributions. I wasn't really familiar with it until we did this work, but the null hypothesis was that the shield had no effect. Our p-value was 0.006. We did a lot of other tests, like changing how many outliers we filter. If we filtered, them to a high degree or a low degree, didn't really change the effect. This is the cutoff here that we're showing of cutting off these outliers. Didn't really matter. If the data are shuffled between shield up and shield down, then there should be no effect. And in fact, that's what we concluded from the data doing the same analysis. So we have a lot of confidence that this very small result is actually significant. Okay. Now I mentioned already that there are some other groups that are doing resonators and qubit measurements underground. And one that's been published recently is from Laura Cardani, Johan Popp, and collaborators, where they're using the underground facility at Gran Sasso in Italy and comparing that with above ground measurements at Karlsruhe as well as in Rome. And these were resonators, not qubits. But what they saw is that they would get these bursts in what they're plotting here, which is the reflection S11 off of a resonator. And that reflection would, change by, basically pi phase shift. And they attributed these bursts to the absorption of ionizing radiation. And you can see this is happening as a function of time. And then when they go underground, these bursts become much less. Okay, and there's some interesting things there. They didn't decrease as much as they would have expected, so maybe there's another source, and so very interesting work there. And now with the NQI, there's efforts at Fermilab as well as at PNNL to use underground facilities to continue this type of research. So just to give a high-level conclusion, radiation, disionizing radiation creates quasiparticles. We measured about 7 × 10⁻⁹, or inferred that value. That's quite close to what we measure as the background anyways. It was roughly 50-50, maybe 40% due to cosmic rays, 60% due to the background nuclear decay. That may be partially our lab. The exact ratio may change depending on what your concrete is made of. It'll limit T1 of our transmons to around 4 milliseconds if we don't do anything. Right, and I didn't mention it, but it also reduces T2. It causes dephasing, not just a reduction in T1. So what can we do? Well, we showed that lead shielding reduces the effect of nuclear decays, so that's true. We can also move to an underground facility that will reduce the effect of cosmic rays, but may be less practical if we're thinking of creating an industry someday. So what we're focused on now, I think it's very interesting to do the physics underground, and we'd love to be a part of that. But we can design qubits that are less sensitive to quasiparticles. And that's work that we're doing right now. Again, if you remember at the beginning, we talked about how we can design qubits and design their sensitivity to different types of noise, and we can reduce the sensitivity to quasiparticles. And the other thing we can do that's pretty interesting is gap engineering, either to trap or reduce the number of phonons in the material and or the number of quasiparticles. And since quasiparticles and phonons scatter between each other, reducing either or in fact both of them hopefully will make things better. So even in the presence of this radiation, the quasiparticles that are generated are swept away from the qubit region where they can cause a problem. And if you'd like to learn more about this work, it's published here in this reference now. And so I look at the clock and I realize, as usual, I took way too much time going through this. It's 11:45. So I'm unfortunately going to skip the last part of the talk, and let me just go on right now and talk about just in 5 minutes this experiment that we did related to waveguide quantum electrodynamics. So cavity, just by way of review, cavity quantum electrodynamics, or CQED, we know is an atom in a cavity. And when we put an atom in a cavity, what the cavity does is it protects the qubit or the atom from dissipation to this environment, which has a continuum of modes. In a sense, the cavity is changing the mode structure. It creates cavity modes. And if your atom is on resonance with those modes, then you get an enhancement of spontaneous emission to them called the Purcell effect. But if you're detuned from those modes, then you're far off resonance, and this effectively protects your qubit. There's no mode that you can spontaneously emit into that's resonant. Okay. And this is a dominant architecture for qubits today. Now, there's another architecture called Waveguide QED, and this is where you couple qubits not to a cavity or transmission line, but just to an open 50 ohm waveguide. Now, that's interesting because it allows you to study qubits in the presence of strong dissipation, and you could do quantum simulations of open systems. And that's true, but that's kind of a happy story, because the reality is that if you couple qubits to this waveguide, you basically just emit photons to them. You lose your energy very quickly, right? And then you say, well, that's what I was trying to study. But the reality is that it's tough because you decay so quickly. Now, on the other hand, we know that in a quantum processor, we're going to need to take information from one part of the processor to another part. Those, classically we call those interconnects, and we need a quantum version of interconnects on these chips. And a 50 ohm waveguide is a very natural way to guide waves from one part of the chip to the other. And much better than a cavity, because a cavity with mirrors means that the qubits might emit their quantum state to this cavity, but then it's going to bounce around a while and slowly leak out of the cavity. So that doesn't make a very good waveguide or interconnect. So this is the way we want to go. But the question is, how can I have qubits attached to it and have them not just give up their energy, have them have a high fidelity quantum state, which I then release and send to somewhere else on chip. Okay, and so that was the point of this work, which we call giant atoms. And I'm just going to briefly show the results here. So a natural atom is small, the ones that occur in nature, compared to the wavelength of the light that we use to drive a transition. And that allows us to impose the dipole approximation, where, at least classically, we can think of the dipole following the field. And qubits are this way, superconducting qubits. We attach them to, say, a waveguide or a cavity at one point, and that is much less than the wavelength of the microwave field we're using to drive it. It's a point-like atom. A giant atom is different. A giant atom, and it's something that we can design with superconducting qubits, is we connect the superconducting qubit to 2 points or more, but we connect them at points which are on the order of or even larger than the wavelength of light. And what that means is the dipole approximation is no longer valid, because, which part of the wave do I follow, right? And what it leads to, in fact, is quantum interference, that the atom, in a sense, is interacting with this driving field and with itself interacting with that driving field. So here's a picture of a qubit. We can just make some wires and connect it to this waveguide at distant points. So this is the sample that we have, and there's 2 qubits, but let's just look at qubit A for a moment. This blue here is a 50 ohm waveguide. It's terminated on both sides with 50 ohms. And if I just coupled the qubit to this waveguide at one point, the T1 would be very fast, right? It would be a short T1. I'll show you in a moment. But because we connected at 2 points, in fact, it interacts with itself via this phase. We'll call it 2 phi here. But we can get either destructive or constructive interference depending on the phase. And that phase is related to, of course, the distance between the 2 points, the velocity of a photon at the qubit frequency between these 2 points, which is roughly constant. And of course, the separation is fixed. We fabricate it this way. But the frequency we have control over. That's a knob. We can tune our qubit frequency so the photon it emits will have that frequency. And that's how we tune the phase. So depending on the phase that we pick, we can get, for example, a T1 that's very short. Here's 3 microseconds. That's a decay that's very fast into the waveguide. So it sees the waveguide strongly. Or we can bias the frequency such that the qubit basically doesn't see the waveguide, that due to destructive interference, the qubit is basically isolated, and it has a much longer, 10 times longer T1 time. And we can do that systematically as a function of qubit frequency and show that the decay rate, 1 over T1, gets better and better to this point down here, which is about 32 microseconds in this case. And you might call that a decoherence-free subspace. Now, it's not zero decoherence. There's still all the parallel mechanisms that are local to the qubit, but the impact of the waveguide is essentially eliminated by doing this. And that happens at this point, 2 phi equals pi. Okay. So then you might think, okay, that's neat. What else can you do with it? Well, in fact, you can use the waveguide to mediate interactions between these two qubits. And there are three distances that we care about, the way we've interleaved it, and then one long distance here. And then gamma represents how strongly we're coupling. That's another parameter, but here we're just going to use a fixed parameter, gamma. And when you do this, you see that, in fact, you can have coupling between the qubits, which causes this avoided crossing between one of the qubits and the other qubits. So this coupling is happening via the waveguide. But what's really interesting is that you can tune that, right? So you can tune the coupling strength, but you can also tune it to a point where the individual qubits don't see the 50 ohm environment of the waveguide, so they don't see the waveguide in that sense, but they do see the waveguide in terms of coupling the qubits together. That's really neat. So you can have decoherent, quote, decoherence-free interactions via the waveguide without losing energy to the waveguide environment. Okay, so now we have the ingredients we need to do these high fidelity operations while being strongly coupled to a waveguide. Now, there's a few other things you can do. You can change the number of coupling points that you have and thereby tune the number of decoherence-free points that you have. That's one knob. And the other knob that you can tune is how strongly coupled you are at those points. And you can change, again, the decay rate and how it varies with the phase that you have. Okay, so just to say that you have these knobs that you can use. And of course, you have the distance between the coupling points, which sets the phases. This is at your disposal. And when you do this, here's an example where the decay rate in blue shows 2 decoherence-free points. Here's one at 4.5 gigahertz. Here's one at 5.2 gigahertz. And yet, you also have, the coupling strength between those two qubits mediated by the waveguide. And that's the G here. And so I'm at a decoherence-free point, but I can be coupled strongly qubit to qubit when I bring those qubits on resonance with one another. Okay, so here's the experiment, and this will be the last slide I showed, given the time, is that we can take two qubits, each one is at their individual frequency, so they're not resonant with one another. They're both in their ground state. We take a pi pulse and put the qubit B in its excited state, and then we take qubit A and we move it from its decoherence-free subspace 1 to decoherence-free subspace 2. When we do that, we bring those two qubits on resonance with each other, and they can, interact via the waveguide. They exchange or swap information, and that's what we're seeing in this color plot here, is swapping information back and forth between the two qubits as a function of time. Okay, here's another look at that. And when we do that, we can create, if we go to this point right here, we can create this entangled state 0, 1, minus 1, 0, and do the tomography of that and show that this happens with a fidelity of 94%, which is, not quite 99.9%, but it's pretty darn good. And, there's things that we can do to optimize that. But remember, these are for two qubits, which are always strongly coupled to that waveguide. So that's really interesting. And the idea is that you could then release quantum states like this from qubits into the waveguide, where they then travel to other parts of the chip. I won't have time to talk about this other experiment in Science Advances, but there we showed the generation of a noon state, 2, 0 plus 0, 2. And we're currently working on directional emission, so we can dictate which direction this state goes. And so with that, I regret that I'm out of time and I won't be able to talk about the 3D integration today. but let me just go to the end so I can show my colleagues. Good. So let me acknowledge all of the folks on the team at Lincoln Laboratory, as well as the group at MIT campus, Joe Formaggio's group in nuclear physics at MIT, and the team at PNNL, and of course the sponsors who made it all possible. So with that, thank you very much.
Okay, thank you, Will. Thanks for a very inspiring talk. And I should apologize, I guess, before we move on, is that I knew I could record this, but I forgot this is the first Colloquium of the semester. So I did it halfway through. And
okay, I saw that. Yeah.
Didn't cause trouble. So now I guess we are open for questions from the audience. Please feel free to ask any question you have from Will. You can unmute and ask your questions. If you have multiple questions, I guess we can use the raise hand approach. I'm trying to see everybody. So I guess while we're waiting for questions, I have one question. I guess it's very interesting that you can see the cosmic ray effects on the qubits, right? So in one sense, it's really bad because we want to make better qubits and we don't want them. From the other hand, you can say, let's just use it as a sensor to understand, like cosmic rays and other things. Is that possible?
Oh, well, I think so. And in fact, very large community of folks are using various types of superconducting detectors, in fact, to detect radiation, right? And so the idea that radiation generates quasi-particles and then we can, measure that, including, high kinetic inductance devices, for example, right? Like this is a very mature field. And I think that it's interesting to ask if qubits could be added to that bag of sensors as well.
So let me ask I guess a very quick. So is the qubit a better sensor than, I guess, the other versions, the squeeze and all that, or is not clear?
Well, it's not clear to me because, the qubits, of course, are limited by the T1 that we have, right? And so there are many mechanisms. In this sense, you would have a sensor that's sensitive to radiation. Well, it's actually sensitive to quasi-particles, right? And which are generated by radiation. But this sensor is actually also sensitive to photons in my resonator, and it's also sensitive to defects on the surface of the qubit. And so it's a sensor which measures lots of things that you're not trying to sense. At the same time, it's trying to sense the radiation.
Right.
And so in that sense, I would say it's not a very good detector.
Actually, there is a lot of requests in the chat that can we go to get the tour of the 3D integration, maybe real quickly, to sort of see what we missed.
Yeah, sure. Be glad to do that. They're mostly pictures, so
that's good.
Yeah, let me go back and show some pictures, which is kind of interesting here. So, the short talk or presentation here is that, you need 3D integration because you need to build chips like this, which have larger numbers of qubits, and you can't bring all the signals in from the side, right? And so these are our, fidelities that we have today, and these are chips that we're making, but you can see long wire bonds, right? And so, of course, everybody knows we need to come in from the third dimension. So the way that we're doing that is to basically use 3 chips, each with their own individual functionality. And the reason for that is we don't yet know how to do it monolithically. And what I mean by that is that the materials we use for this readout and interconnect layer, where we have multiple wiring layers and interwiring layer dielectric, this looks a lot like a CMOS process, right? Those dielectrics are very lossy. So we want to keep them as far away from the qubit as possible. And the fabrication processes to do all of this monolithically, at least in our experience, we've tried it, it leads to rather low coherence qubits. So maybe someday we'll figure out how to do that. But for today, we fabricate the qubit chip the way it should be fabricated. We fabricate an interposer to bring signals between the qubit chip and this readout and interconnect layer. And then we fabricate the readout and interconnect layer. And so basically we fabricate them independently and then we bump on them together. So qubit chips go on top, basically face down, right? And then on the bottom, we have this readout and interconnect layer, which is a multi-layer niobium process. So these are metal layers M0 through M7, isolated from one another by dielectric, about 200 nanometers of dielectric. But then you can connect between the layers using vias, just like you would in a CMOS process, right? So the signal can, go up and down and over and around, and it goes, and you do that, you route it until it gets to right where you need it to go underneath a qubit, and then you can bring it up to the top through a TSV, right? So this process also has Josephson junctions. This is a classical Josephson junction used for classical digital superconducting electronics. And it's also where we make our traveling wave parametric amplifiers, is in this process. So this middle layer is the interposer, and this is where we have these deep through silicon vias. They're 200 microns deep, 10 to 20 microns racetrack shape, and they superconduct. They superconduct because we fill them with titanium nitride. And so the tinitride at the top is maybe 150 nanometers. It's 100 nanometers at the bottom, but it's that's sufficient. It's well filled. This is looking down into a TSV. It kind of looks like Niagara Falls or something. And then over here, just to give you a size scale, this is a qubit with this is the capacitor for that qubit. Here's the readout resonator. These little black dots, those are the TSVs. They're tiny compared to the qubit. This would be a 100 micron TSV. That would be a 500 micron TSV. There's some people in the community doing this, but those are just too large because you're going to want many, many TSVs per qubit. So the fact that it's a high aspect ratio is quite important. So the other feature is that it not just routes signals, but it can be used to reduce footprint. And what we mean by that is, look, you have this long resonator, more than a millimeter here. And what you can do is you can build a resonator that uses the titanium nitride and the inductance in that TSV, as well as some parasitic capacitance to this bottom plate here. It's basically a lumped element resonator. And then you put the TSV underneath the qubit, but you don't galvanically couple to it. And so it's capacitively coupled. And when you do that, you can read out your qubit. And here's just 0 and 1. I'll show you on the next slide. This just shows readout of a qubit in this format, right? Where we're bringing signals in through the TSVs. And then there's a TSV resonator that we're probing, and we read out the qubits ground in excited state with about 99.8% separation fidelity. And if you ask, does it impact the T1 of the qubit itself? Here's the T1 of this device. It was about 40 microseconds. And so there may be some impact due to the presence, but it's very minor. And likely we can design around it. Maybe the resonator was too strongly coupled, for example. So basically that was the quick walkthrough of the 3D integration.
Thank you. That was fantastic, actually. So I guess Matt and Ken have questions. Matt, do you want to go first?
Thanks. I think Ken had his hand up first. So Ken.
Oh, sorry. I didn't check that. Ken?
Yeah, thanks, Will, for the great talk. I had a question about the T1 times in the very beginning. So,
okay.
So from cosmic rays, let's say. So you showed that the rate from the T1 from cosmic rays is on the millisecond scale.
Yes.
But the rate of any individual cosmic ray hitting your detector must be quite a bit smaller. So it must be somehow that the cosmic ray makes many quasi-particles and they're sort of long-lived, right? And that's encoded in this K. But my question is, what can you do to, or can you do anything to make, I forget the right sign, I think K smaller. Can you make the quasi-particles shorter-lived?
Yeah, so that's a great question. And let me just emphasize, it's not just the cosmic rays, but also the nuclear decay events from the concrete walls or anything.
Radioactivity. So for example, if you could make it short enough, then you could, maybe have a muon veto or a radioactivity veto in your device.
Yeah. So the way that we can reduce this is basically by either going underground, right, or shielding, or we can, what we would like to do is design phonon traps and quasi-particle traps so that we can enhance the recombination rate so that even in steady state where we have radiation coming in, quasi-particles are being generated, but they're either flushed away from the qubit region, or in fact, maybe they're trapped, or we can enhance their recombination in some other way. And so by doing that, we reduce the impact on the qubit. So that's one way to do it. And then the other way would be just design a qubit that, doesn't listen to the quasi-particles, doesn't hear them. It's less sensitive to quasi-particles. And I think it's going to be some combination of all of these that just beats down this effect, right? We get another factor 10, now we're talking about 40 milliseconds. That'll buy us a few more years. And, it's this type of mentality.
Thanks. Matt, you want to go?
Yeah, so actually my question has to do with the same part of your talk. You had these unknown parameters, like for instance, the conversion rate from radiation to quasi-particles. Can those be computed? Is there a way to compute them and compare it to your results?
Yeah, there is. And in fact, I showed a link to a paper by John Martinez, which came out in December, where he ran through some of those calculations based on work by Steve Kaplan back in the mid 70s. I think the issue for me is you can do that, and I'm glad that he did it. When we started this, maybe we should have done it in hindsight, but when we started this, we didn't know a lot of the factors that went into that. And there was just a lot of unknowns, and it wasn't, we get an answer, what do we do with that? And so we approached it from this other direction of let's use a calibrated known source of radiation, get some idea of what is the impact, high levels of radiation on the qubit, so that we can understand, this conversion of absorbed power to T1 time, and then use that and see if it's predictive. And it matched, parameters that we observed, like the background non-equilibrium density of quasi-particles, or quasi-particle fraction. So there was, some self-consistency tests we could do there. And now we do have a program actually with PNNL where we want to go back and test, these individual scattering mechanisms and rates that lead from radiation coming in to, through that cascade down to the quasi-particles being generated, through phonons. And so we would like to nail those down piece by piece. Yeah.
Thanks.
That's amazing. Let me see if there is any other question from the chat. Yeah, I don't see any, I guess. Yeah, thank you. Thanks, Will, for this fantastic talk. It's always, I always enjoy listening to your talks, and there's always something new and phenomenal happening. So, no, absolutely. If there's no other question, I guess we conclude this colloquium and thank Will again.
Yeah, well, thank you for the invitation. I really enjoyed it. And,
Our pleasure.
I look forward to post-COVID era when we can actually go get dinner together in New York City.
Exactly. No, we will do that. Yeah, thank you. Have a great one.
Okay, thank you. Take care.
Thanks, everyone. Bye.